Hello everybody, welcome to another stream. How are we doing? So last stream we got the final shader working, which constructs the BVH into a traversable data structure. I guess the other one could have been traversable, but this one's more optimized to traverse. So this is the tree that we've built on the GPU, and every leaf node has an ellipsoid. Every node has the potential to have, every internal node has the potential to have up to 4 nodes as children. Yeah. So hopefully we'll be able to get some ellipsoids or many ellipsoids rendering, because we saw we had an ellipsoid, but this is just one being ray traced against as a proof of concept. All of these guys come from being randomly created. Hey Glorious, good to see you. How did the did you sort out that problem with raw input? Are you planning on using raw input, or are you trying to get or deal with the HID raw thing? What are you trying to do? What API are you trying to use? So I think before I carry on with my implementation, or sorry, actually start on the BVH Traversal, what I would like to do is just double check to make sure that everything is working fine. So currently we build a tree randomly, and we've tested a bunch of different random. Like we've got a fixed seed, but we changed the seed, so we've tested a bunch of different random BVHs. But my problem is we had a hard-coded 64 leaf nodes. So I just want to reattach it to my slider again and have a bit of a play around with that one. So I'm just going to go ahead quickly and just replace all this. It's a bit too many, I think, but anyway. So ellipsoids count. So maybe we can abstract into a function as well, because I think we want to get out of the main function, I think. But yeah, so we have the count on a slider. Boom. Alright, let's just plop it in here. Generate all those random ellipsoids for us, please. Maybe I could add the ellipsoids count to it. You know, I'll put it up here in it. Add the ellipsoids count. Make it stack. And we'll start off with like 32 or something, I don't know, 16. So we make that the configurable thingy. Now, and I guess I can just drop that in. Have we signed it? And we'll make a leaves count, which is just a ellipsoids count. Alright. Random seed, randomly generate. randomly generate all these guys, ellipsoids count, upload to GPU. We'll have more than one. Do stuff on the GPU. Yeah, I think I might move this into a function that builds the BVH. Or maybe it's a bit too early to do that. I used raw input and I lived in the rare event. I lived with the rare event using for some time. But when I finally decided to investigate, I found the problem that I described in the Discord. Yeah. I switched to raw input usage like you were doing, right? I don't know how to compose the previous sentence correctly for some reason. Yeah. No, I did stay up with the chat. Yeah. You just tried to do something that was a bit yeah, that was not very well. There's not a lot of examples on how to do it that way. But yeah, the Windows event loop is really weird. It's just so bizarre the way it behaves. I still haven't got the resizing working in mine. And that, yeah, the resizing and the moving. I think I've done it in a very hacky way. When I get the multiple threads working, and I can be bothered to get my graphics to resize, like it's not so bad doing it. But I just haven't bothered doing the work. But when I can be bothered to do that, then I'll probably fix the Windows thing where, because right now I can't drag the window without the game pausing. I think that's the way it works currently. I might be confused. Right. Sweet, now we've got the updated version. But it's not rebuilding the BVH on the GPU every frame that we do this. So we can do that. What I would like to do is make a new function. So effectively we want to be able to build a BVH. BVH build. So that's got to remember. So there's a bottom level which needs ellipsoids, right? So but the ellipsoids is only needed at the right ellipsoid indices buffer. Interesting. Yeah. So that could be an instances indices buffer, maybe. Or that'd just be, yeah, instances, wouldn't it? For the top level BVH. Maybe I shouldn't bother reset. You know, I won't put it into a function yet. What I might say is, I might make a boolean to say, oh, it's changed. And it needs a rebuild. But also I could just rebuild it every frame. Yeah, for now let's just rebuild every frame, because then we'll be able to see like, oh, how long does this thing take? I gotta make sure though that so put it in stuff like this. So we'll move this into a function when we need to do the top level. I'll figure all that properly. So rebuild every frame. And what I would like to do is there's a thing called next node. It gets set in frame minutes of 4. And we need to make sure when we are finished building the BVH, so we've reached the root node, I think. Is it this one? Yes, one that reaches the root node. Right, if root node, we'll plop it in there. We need to make sure we sync on that buffer, I think, though. Because it does the atomic adding in the next shader, build quad tree, so build binary tree, we'll reset it here. Right, reset for this shader to use, right? Awesome. So that's all done there. Is there anything else that's missing? Because it could... Oh yeah, I've got to put the sync code. So build binary... Oh, I've already done it. Yes. Did we put the sync code for that on the... No, that needs to be there like that, doesn't it? And then in pack quad tree, do we do anything with the globals? No. No, nothing with the globals. Sweet. That's alright, isn't it? Right, so hopefully this runs and it didn't just break it. So we should be able to drag it and change the size of the BVH on the fly, and it will get what's the word? It'll get rebuilt every frame. So we should be able to see in the debugger now. Well, not debugger. In the profiler. Right, let's get rid of that. Then we can enable the profiling. And we should be able to see that in the console. And see how fast it is. It's not a very big tree, so it shouldn't be that slow. But yeah, the plan is not to really build BVH as much. The plan is to have them built when you have finished editing the model, and then we only will rebuild, we'll refit animating models, and we'll build the top level BVH every frame. So that should be alright. Absolutely weird, and I tried checking people's repos in GitHub. They use buffered or input, and they were either disable this code path or do things as I do, so no help. Huh. Yeah, I guess many people try to use the API. There might be some really obscure blog post on the Microsoft website or something that you need to find. Yeah, there's some stuff you can do on Windows that's not really well documented, but there'll be a blog post on it, and you'd be like, wow, you can do this? Yeah. Interesting. So is this a detour from your audio stuff that you was working on, or is it kind of related? If the stream dies, I'll be right back, but it shouldn't do, right? Here we go. Okay, we're still alive. That's good. So we've got the... Right, so the Morton code uniqueifier runs. Look at that, lightning fast. Well, it's only got 64 things to... or 32 things to look at, so of course it's going to be insanely quick. Build binary tree, that's there. The quad tree takes longer, and then packing takes... Wow, building that quad tree, that's interesting, it took that long. Oh yeah, it does, there's that search it has to do in the parent node, which we could probably optimize away. Yeah, maybe that's something there. But yeah, as we increase it, we should see the time. Yeah, so if we decrease it, they're basically instant. And as we increase it, it gets a bit more noisier. But yeah, that's cool. So that's 64 nodes. That's about 32. That's about 4 nodes. Right, so at least we got it at a point where it can, you know, we're technically building multiple BVHs now, but we're rebuilding the same one every frame, right? So the whole system that builds a BVH doesn't just, it gets reset properly, basically, right? So that's good. Cool. So as we're moving it, we're not seeing any printing coming out, I think. Let me quickly disable this. So there's a print in one of the shaders here. Pack quad tree, and it's if not all of the nodes have been allocated properly. And that happens in the previous shader. And then it returns early. So we want to make sure we don't hit this. So what I would like to do is actually enable it first. Actually, no. I don't want to enable it first. Let's just run it. I haven't got the profiling on, so we should see it pop up, right? We don't see it. If I move this around, we're not seeing it either, right? That's good. So we've changed it across multiple different seeds, and now I've moved it here, and I cannot see it printing. I want to just show you that it does print out if we enable it. And then, so print out like this, right? See? That's cool. So let's quickly just change the seed one more time, and then we'll just get straight into traversing. So I'm just gonna, knock a couple of digits out, whatever. Oh yeah, the seed changes with the count. I did that. That was a thing. So we already have tested multiple seeds. Sweet. Right, so that should be building a correct BVH now, which is cool. So let's start with the traversal. So we're going to actually ray trace a BVH now and hit the ellipsoids. So here's the ray tracer we've built already. It just ray traces a single ellipsoid, but it doesn't ray trace against any bounding volume hierarchy. So we're going to start that now. So this is the push constants that we upload to the shader. We obviously need to have access to the nodes, and we obviously need to somehow know which BVH we're rendering. Yeah, because you always want a reference to the top level BVH, but we haven't got top levels yet. Right, the top level contains a tree of instances, right? But we don't have instances yet, so we don't really have a top level BVH. So we just have we just have a single bottom level. So we're just gonna know, we just need a reference, BVH, node index, I guess. This would be the root node, right? So read only on that BVH node buffer. And that should be it. We are already rendering with that shader. So let's go ahead and find where we're doing that. So it actually accesses the irradiance map, the environment map, and the pre-filter map and all that stuff, right? But we also need to... It accesses those via some global indices. Yeah. Rather than passing them in. BVH nodes buffer. Then we want to synchronize it for read only, like so. So we're missing one more thing, and that is simply the BVH root node index. So the root node index is 0. We'll slap a nice to do on there. To do replace with top level BVH index. So depending on our game rate, we might not need to support different top levels, and we could probably have it in a fixed location. if we wanted to do that, because it's built specifically for this game and stuff, but we'll see. I don't see why it's not that hard exposing just one integer for it, right? But yeah, so we need to replace that. So now we've got it in the shader. What can we do? So we don't have a root node actually. So the way our system works is we have our BVH node, and it's this super lovely packed data structure, which is all nice and good for the CPU. So there's 16 bytes here, 128 bits of information. So we have up to 4 children. Yeah, we have up to 4 children to a node. So there's 4 siblings. So the 4 siblings sit next to each other in memory, so that fits into a single cache line. So I've just remembered 2 things that I've forgotten. So there's 2 things that I need to do before we carry on. One, we need to make sure that it is aligned to a cache line. 64 bytes. We need to do that in the Vulkan backend. And the other thing that we need to do is we actually need to make sure that we keep the number of children in the node. And I forgot to do that. A bit of an yeah, I just completely forgot. So when we ray trace against it in the shader, what we have to remember is multiple threads are going to be going down the same path. And if all the threads in the same path come across a node, or go down the same node, or come across a node with the same number of children, then it will end the for loop quicker. That's the hope, right? So it will, in this case, it has to go over this one and that one, and then take note on how well it did, and then store the results somewhere, I think. I think that's the idea. If not, it will have to look at the node over here and the node over there, and they'll just be in some invalid they'll be like 0 basically, so they would always fail. So we should probably squeeze in a couple of bits to keep note of how many children there are. There's always going to at least be 2 children. So there could be 2, 3, or 4. So you only really need, you still need 2 bits. So the easiest place to take 2 bits from is this thing here, which is this with this index. So I'm gonna just take 2 bits off here and just children count. So we'll go ahead and quickly add that into the BVH node. Change the construction code a bit. So this is the packing code. The Y is 20 apparently, isn't it? Wait. Sorry, that just feels incredibly wrong. What's going on? Why is it shifted by 20? I don't know, what did I do? That is 20 bits, so I said. I completely read something wrong and I just did the... Right, so I'm glad we've come back and looked at that, because we would have got invalid indices there. Yeah, we've got to put some safe code in to make sure we're doing the right things. Yeah, these all look good, I think. 1024, yeah. Yeah, these are all right. It's just this one that was wrong. So Y is how many bits? 12 bits. So we need to move that by 12. It must be 14. and then it will fit 18 bits there. Nice. Right, that was silly. So that's good. We just got to make sure we correct the ref index then. So children count has to be children count take 1. Wait, is with a parent? Yeah, always just be take 1. If not, it won't fit in. Because you get a 4 and it won't fit into 2 bits, right? 0 to 3 inclusively. And then in here, we're just going to pack in 0. You have 0 children. What the crap is going on here? What did I do? Oh yeah, I did these things. Right, nearly there. So I just got to do the unpacking code. So these are actually shift right by... It wasn't 20 bits, right? It's shift right by 14 bits. And then we need to add a new one, which is children count. Which is shift right by 12 bits. And then we take an and. And what we want to do is, so we get the first 2 bits, and then we add 1. So it's only valid for when it's equal to parent, isn't it? So we want to say if, right, nice. So that should be all right. We just got to go ahead and fill that in. So we do that BVH node in it, which is here. We just got to put in the children count, which we can always work out. So in this case, here it's going to be a bottom level leaf, says no children. This one, well, it's always going to do take 1 on it, isn't it? No. Oh, we want to do the take 1 in here manually, isn't it? Yes, it's number of children take 1. So where's the children? Oh, it's there, isn't it? Right. So we take 1, so it fits into 2 bits. There we go. I guess we could always do the take 1 inside. You do the take 1 in this, actually. You always do it here. And you have to AND it with 2 bits. If not, the value is going to be too big. Yeah, if not, the value is going to be too big and mess this up here. The rest of them, we didn't have to worry about that because they've already been guaranteed to be clamped. Okay, so that's more sensible there. Cool. So let's get that compiling. Give another run. Hopefully the stream doesn't die. Maybe sanity check assert for the minus equal 1. Yeah, but this isn't on GPU, so I can't really assert. Yeah, I can kind of maybe build asserts, but they'll be triggered later on the CPU. Yeah. Hey Silvercore, how's it going? But yeah, I could put an if statement in here like this and do it. But yeah. Yeah, there's something up with my GPU. I don't know what it does. It gets so noisy sometimes. I might have to start either have to track down that problem, figure out what it is, or you know what it is? That's probably just the draw 2D shader just being really unoptimized. I don't know. It's probably a few things, to be fair. That's cool. Right, that all works fine. So the other thing we want to do is cache line align our lovely buffers. So I just want to cache line align everything because I got an engine folder now. Because we're doing a game without an engine, but we've got an engine folder. Because it just makes the most sense. So in the Vulkan backend, where we do the memory allocation for the buffers, we should just cache line align it all. So you do your, it's right about here, right? You do your get buffer memory requirements, and in here, this one, there's an alignment. And we just throw it right in there. Yeah. Right. It already will be aligned to 6. Yeah, because allocate memory doesn't take it in. So it already will be aligned to 64. Because we don't sub-allocate. Yes. So there'll be a base allocation. There'll be like it'll be to like a page or something like that. Like 4096 or 64K, something like that. So that's okay. So it already is aligned. That's good. That's all I wanted to know. Right, so now we get back to the traversal. Ray trace, BVH, ray trace. Okay, this is where the fun begins. So remember what I said where the nodes are, all of the sibling nodes are next to each other. When you look at this graph, you'll be like, oh, there's a root node. But the root node is a lie. The root node does not exist. After we've ran BVH pack quad tree, it looks at the build quad tree and it just chucks the root node out of the picture, and it puts all siblings next to each other in memory, and it will waste space if there's only 2 siblings in there. So they're all in a cache line. If you got 4 of them in there, they'll all be in a cache line together. So this means that this node and this node will be at index 0 of the BVH. So we should be able to look at 5 and 6 and render them. The only problem is that the coordinates are probably quite crazy. So we could probably look into... The coordinates and sizes might be quite crazy. And random. So we should probably look into doing something about those things first. Keep finding new ways to not doing the ray tracing, you know? So we should probably figure out like a good... You know what, they'll be in a normalized space. So we'll be able to see it in a small area on the screen. That'll be okay. Yeah, not worth the extra branch, man. No, I think it's more than that. Yeah. What I should really do is if-def, have if-def assertions, and have a lot of them in the code, but I've not bothered doing it yet. But yeah. So I can compile with them and without them. And that would be super great. So let's get the BVH node. I don't know how I want to do this, but let's just say, right, so we're probably gonna have some kind of while loop. You know, let's make it a for loop just in case we, you know, go absolutely crazy. We'll call it iteration just because there might be other for loops within here. So we say iteration is less than, and let's put a cap on it at probably 64k. All right. So what we need to do is access. So I think let's just render. For now, we'll do a break, I think. For now, let's just look over all the children of a node and just ray trace against those. And then let's just... So I forgot how we ended up doing it in our previous one. I think we took a path down the tree. I think the way we traversed it in the past is we took a path down the tree. If we hit this one, we just go, oh, I'm going down here now. If we hit this one, oh, I'm going down here now. Right? And then I see if I hit that, no. Yes, I hit that one. Then I go up, look at the sibling, you know. Oh, I hit that one, go into here and test. And then you sort of come back up and then go over here again. I think I want to try something different, where maybe we keep the result of if you hit something. And do the tests as and when you have fetched the memory, because you're going to have to test them anyway. So I'm trying to think if I could probably keep the result or enough of the result, if that's possible. Yeah. So let's just say we're going to get the node, BVH node, BC BVH nodes. Is that what it is? All right. So you have your root node index. I guess we'll just, I don't know what we'll do, but something like, yeah, you'd have to keep a bunch of indices around maybe. But yeah, let's just do something like this, right? So, yeah, we'll read that out. Then we can read everything out here. So get the number of children. So there should be 2 children here. This would be BVH node children count. So it just extracts that out of that. And we go over those 2 things there. Now, each of these nodes within here are going to be... Oh yes, this one has to be a parent as well. So I'll do a whoops in here. We'll go, oh, this thing must be a parent, right? Oh, did I delete something? Yeah, so we want to say node type. BVH node type parent. And if it's not a parent, whoops. Node type is not. And then we'll say got. All right. Okay. So the next thing to do is somehow get access to the child nodes. Wait. I didn't want to go down to the child nodes yet, did I? Because at this root node is going to hold the number of children at that root node. Crap. In the root node index, we should probably store the number of children in the high bits. First, the top couple of bits. So we should probably say right, so maybe we can make a new type and call it BVH reference or something like that. And then we can just, yeah, I think that'd be a good idea. So when you create BVH, you get back a BVH reference, perhaps. So it'd just be something like this, right? And you just say, so it takes in a root node, index, and the number of children. And you would just basically pack it in there. So the children, the children could just go at the front, to be fair. So you just go root node index 2 ORed with this, take 1 and a couple of bits. And then we have a way of extracting that out. So ref would just be shift right 2 to get the root node out, and then to get the children count is simply hold on a minute, which would be ref and just like that. So this is something we can now pass up. What is that to do? In the ray tracer, right? So here we're going to hard code it. So ref root node 0, and it has 2 children. Well, we don't actually know the number of children it's going to have. Maybe that has to come back from the oh. So I drag the slider in that. It's going to mess up now. Yeah, so the GPU will know. Maybe the GPU has to send you it. Yeah. Well, we could just always search. I don't know. Let's just hard code it for now. We'll figure out that problem in the future. Future problemo. Yeah, maybe we won't have this thing. I don't know. But anyway, BVH ref root node. All right, and then we want to do something like I don't know what is children count. Right, there we go. So we basically just want to say go over the number of so this is our the start index for the What do we call it in here? Children node start index. Guess we can call it that. Right. So we're going to go over these two nodes, I guess. Plus child index. So let's just get these out. I'm not really fussed about knowing what this is at the moment. But we can at least try and just render the thing. So we're going to get out the center position. This is going to be inside norm space. So I've got to figure out how to get that. That might just be local space of the object, or it's going to be the top level one and then be in view space. So then I need to convert that some more. But since we're just trying to read stuff out, we're going to just have a region in the world where we're just going to view what it looks like. So I can just do BVH node. Well, I thought I could just do that. Node center. Ooh. Oh, node ellipsoid. Yeah, so I can pull that out. So decode it from the node. I can also pull out the half extent, half dims in unorm space. All right, and there's also like rotation, but I'll tell you a bit of a, we don't really have rotation until you reach a leaf node, and we probably won't be able to test it anyway until we have an editor, so I'm probably just going to leave it alone for now. But we can extract it, so at least we know it's there. To do only for leaf nodes. By the way, to do use this, and by the way, it's only for leaf nodes. Right. So now I think we have all the information we need, right? We need to transform into the local space of the ellipsoid. So you would do the rotation to the ray. So your ray is up there. So you want to say like ray local space, basically. You take it from world. So you'd be like, let's just apply it here. Let's make some stuff up. So ray direction local space. So do a multiply. Wait. Yeah, multiply. Yeah, multiply vector. Quaternion. So with the rotation and your ray direction in world space. And then you would apply a translate and a rotation. I forget which comes first. We'll have to figure that one out. But wait, so the origin. Wait, is there an origin? Okay, you pass in the origin. So I guess what do we do there? Yeah, we use the origin Oh, right. The ray origin is, yeah, the ellipsoid must be at 0, 0. So you'd rotate the origin and you'll position it. Maybe get some drawing. Maybe draw it out. So you have your ellipsoid here, and your camera's here, right? And the ray's obviously coming from here, so the origin's up there. So you need to draw a vector from there to there, but there also needs to be some rotation to it as well, right? So you probably do the trans. Yes, I think what you'd do is you'd say you'll compute the origin in local space by doing the subtract. So you go towards ray origin in world space from the position of my object in world space as well. So for now, we'll just go. So what I would probably like to do is just make up world space versions of these guys. And I'm just going to do a complete copy of that. Browsing, thank you so much for the sub. Appreciate it. Welcome back. How you been? Appreciate it, sir. So this would then just be, yeah, we're just not going to bother changing anything. And then let's just go ahead and produce the from world space. Yep. And then we'll apply the rotation. So you rotate yourself because you'll be relative. Yeah. Right. And then you do your ray tracing. Local space, local space. And then the radius. There's no scale, so it's be half dims world space. Maybe we could put a bit of scale in there, but I've only got so many bits, you see. Well, the scale is the half dims, that is the scale, right? So yeah, I don't need a scale. And then here's the ray trace against the ellipsoid. So now it should just be a copy and paste of the shader code. So yoink. So this is the old code, let's nuke it. And so, right, let's review what madness we've just created. So we're just looking over the first top two nodes. That's all we're doing. And I've bothered to set up an even bigger loop for some reason. But we're just trying to see what the first top two nodes look like. And obviously we shouldn't be rendering these guys. These are going to be parents of much smaller nodes. But yeah, we should be able to see these at least. Right, apparently it's all compiling. So let's just make sure we haven't done anything too dangerous. Oh, no worries. Thank you, thank you. Appreciate you too. Yeah, so get the number of children, we pull those boys and girls out. I should really double check and make sure those are all written correctly. So we shift left, yep, all that with that, yep, and 3, yep. 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 Legit. So we pull that in. We've got many iterations, but we break, so it should probably get compiled out anyway. It doesn't matter. We go over the first two children. Right, we'll pull them out. I've commented that for a sec. We extract the center position, the half dims, and the rotation as well. I have plugged it in actually, so there's no need for that to do label. We'll just know it's broken when we try and use it. I don't know which rotation to store in. Either it has to be the one which rotates us into the local space of the object or out of, and then we have to either invert it in some cases because I use it in some other place as well. So yeah, it has to be tried, and we have to somehow convert into some world space, or maybe, yeah, that's stuff to play about with, because we're going to have a top level and a bottom level traversing code. So our ray direction in local space is rotating the ray direction in world space, and then yeah, I don't know if you need us. Yeah, it's fine. Then so you don't need to apply a scale because it probably does it in here. Then you go a direction towards the ray origin from the center position of the object, and so this is going to be a vector going from the center of the object towards the camera now. And then so our ellipsoid is now at 0, 0, 0, and then we rotate this origin as well around the center. So then our ellipsoid will now be axis aligned as well. Well, the ellipsoid is always axis aligned in the middle, but we've moved the ray origin such that it is as if it was the ellipsoid that rotated, if you will. I don't know. Anyway, yeah, we just change spaces basically. And then we just reverse ellipsoid, and then we run our shading code, all the PBR lovelies. So, all right. So the problem with this is the shading is going to be a bit buggered, because I've got to translate it back into world space or whatever to do the shading. But we don't have to do that. We can at least just see if we hit something. So let's see what happens. If the stream dies, we'll be right back. Here we go. All right, well, some balls. Get out of the way, tree. Right, and oh, crap, they're so small. Right, progress. They're a bit flat as well. But as we change the tree, you see the shapes of them are changing because they've got to encompass more nodes, they're getting bigger. Right, that's interesting, isn't it? Because these are parent nodes, right? These two here, there's two balls, are this one and this one, right? Obviously, when we have 4, it's going to be this one and this one, because I've said from the CPU that there's only 2 nodes in the root. So it seems like we're getting some good results. When I make it very small, some of the ellipsoids are actually very tiny, and that's because these ellipsoids must be only big on one dimension, but I am seeing a bunch of little ones. Oh no, sorry, that's the Morton code, that's the positioning. Yeah, so it must mean because they are literally disks like this as the random number that generated it. Right, that's interesting. And obviously these ones get bigger because they've got many other ellipsoids in here. Right. Cool. So that's good. So how are we going to traverse? See, I'm thinking more about this reference thing. You know what? Let's just leave it as it is. So how do we go down another level and render everything at level 2? No triangles. They're banned. I've considered putting triangles in for certain algorithms, but it would have been software triangles. But yeah, no triangles. So the idea is to try and use nothing but compute, And basically where it's fallen down to is if it's 2D, it's either tile, basically it's sign distance fields, and I just tile bin stuff if I want to optimize it. But equally, it doesn't have to be sign distance fields. I've got quite a complicated sign distance field renderer though. Pretty powerful, but also it has a bit of performance hit. But then if it's 3D, you basically have to ray trace it. There are probably other things you can do with like atomic mins and maxes and stuff, but you're better off with 64-bit ints when you got those. So yeah, ray tracing for 3D, sign distance fields for 2D, and tile bin for 2D. So 3D you can do a few things like BVH trees and that. I guess you could do that for 2D as well. But yeah, you need some form of custom acceleration structure when you do stuff like with compute. Yeah, it's pretty cool. No worries. Right, should we listen to the newer Nick Johnson album? It was quicker to go back than let it load. Anyway. So that's really nice. So how are we going to do the traversal and go down a level? Because as soon as you kind of get the code going down one level, the rest kind of fall into place, I think. Well, unless you hard code it, right? But we're trying to think of something that's scalable. So let's bring back up the tree, because otherwise it's just me imagining stuff. So remember I said the previous algorithm I used to do went down the tree. So it was like, have I hit this? No. And then goes to sibling. Have I hit this? Yes. Traverses in. Have I hit this? No. Have I hit this? No. Have I hit this? Yes. Traverses in. And it tests against all the siblings, comes back out, tests the sibling, goes in. So it's as if it's like executing code, right? It calls a function, goes in, does some stuff, pops back out, right? In a sense. It's like a stack. And it followed. But because I've architected my stuff to fit into cache lines and things, maybe it's better if... Oh no, it definitely would be better, right? Because this is a very small tree. So you'd be like, oh, yeah, but the whole tree fits in cache. Yes, it does. But when you have a bigger tree, it won't fit in cache. So you might have a really deep set of nodes here. And by the time you come back up and look at these guys again, they wouldn't be in... yeah, and test against it again. The result won't be in cache. So you bring up 4 nodes into memory again. But can we keep the state in local variables? That is the question. Because you'll use a bunch of VGPRs or SGPRs. The alternative you've got is LDS memory, which means you will cache the result in some form of L1 cache explicitly. So you've got group shared memory, you can also stuff it in there. But you only get so many of those per threads. Sorry, it's shared across the thread group. But when you... Yeah, it's shared across the thread group. And if you use more and more LDS memory or group shared memory, you will limit the number of shaders that can be paused in the compute unit, and it will go and work on another shader while it's waiting for the memory to be read back into the cache. So it has this sort of... Shaders have this system where your compute units can have up to about 10 shaders which can be running, and if one shader gets to a memory read or write or something like that, and it has to wait for the result, it will switch out to another shader and just run that code because it's ready. So if you have tons of group shared memory, you limit the amount of shaders that can run, because it's had to reserve a whole block of memory in the compute unit. for the group shared memory. But you've also got the same thing for VGPRs and SGPRs. So every one of these variables, if this is the same across every thread, it's an SGPR. If it's different across every thread in a compute unit or in a wave, 32 threads is a wave. So one SIMD unit, that would then mean that's a VGPR. So you only get so many VGPRs again before the compute unit needs to reduce the number of shaders it can switch between. So we need to be careful. We've only got so many VGPRs and so many SGPRs, and also so much group shared memory. They're the places in which we can store stuff, and where we can store some of the information. So what information do we need to store in order to be able to go back and carry on with the traversal? So if we hit this one, test it, have we hit it? Yes. Hit this one, have we hit it? Yes. So we essentially need to store our yeses in a buffer to come back to, right? And when you have a yes, all you need to know is what you need is a node ref, right? You need a child, start index, and how many children are there. When you have that, you can always come back to it. So I think we just need a buffer, and this would mean that when we're really deep, we can always just pop back off the stack and just jump up. Like, imagine if we had just such a deep tree. Right, imagine if we're here on 83. And imagine we didn't hit this one, we didn't hit any of these anymore, right? And imagine if we didn't hit that one, didn't hit this one, but we hit this one, and we need to start searching these guys, right? The code, if it was in a stack, you could go, all right, I've hit this one, and I'm keeping it as my closest ellipsoid that I've hit. But I still need to check the other guys that I've hit because something else could be closer. So it just checks the stack because it's run out of siblings. And what's at the top of the stack? This reference over here with these children. So it just like starts searching these children instead, without having to go up the tree and go along and go down. Right, so it's a nice quick jump to where it needs to look. So I think that's what we should program. So for now, the stack is going here. And sounds like advanced hyperthreading. Oh, you're talking about the compute unit stuff. Have you looked into how the compute unit stuff works, Clarissa? It's proper fun. You should look at the Mali GPU. Yeah, this one. It's a lot of fun. And then there's the AMD RDNA 2. Well, you got RDNA 3 now. Yeah. But yeah, these are good. If you ever like not doing much, or you're doing stuff that you need a video on in the background, and why is these things taking so long? I'm streaming just fine. But this is a good resource. It talks about mobile chips and desktop chips and how they work. That's amazing. I think towards the end it talks about some specifics with ARM, but yeah, you can skip those. And this one is just like the instruction set architecture for RDNA, which is the AMD's processors. And there's also another reference where it talks about the actual architecture, not just the. There's an architecture PDF as well. But yeah, they're around. They're a good read because you learn about how they work. Shader concepts, Wave 3264. Yeah. I guess this has it. SGPRs, VGPRs, and LDS memory. Yeah. So yeah, they're good. Yeah, the RDNA 2 one has 2 PDFs, I think. It's a good read. Yeah, when you look at the hardware, you're like, oh, this has got a bunch of stuff that I don't have direct access to in shaders. You're like, this sucks. Like, the RDNA 2 architecture, should we say, or there's a thing called GDS memory. So your LDS, local device storage, local data share or local data storage, something like that. But they probably anyway. But there's one called GDS, which is global, and basically it's you don't really have access to it, but it's shared across. There's a picture for it. It's here, right? Here's your workgroup processes. It's shared across all compute units. So your buffers obviously live in main memory, and your buffers live, they come into the L2 caches, but they're here. And then I guess they come into this L1 cache as well. And there's some texture cache which goes into L0. But you got this GDS, which is like here, which is globally shared across all compute units at 64K. You don't have access to this, but you have access to this and this. This is group shared memory. So yeah, this stuff, and there's instructions as well, where they've got some really when you really read into it, there's some specific things that you don't have access to, and it's like, oh, well, if only. What is missing is NVIDIA as far as I know. Yeah, NVIDIA doesn't really expose. They expose like some architecture stuff in places, like especially in CUDA world. But yeah, it's not as good as AMD's though. But AMD could be better. It could be more open, right? They could ship their tooling into Vulkan and say, you can pre-compile your shaders and load our binaries, right? I tried downloading their shader compiler so I could get a disassembly of it, because I wanted to see a disassembly of my shader code and see how many VGPRs are being used and make sure that I didn't go over the budget. But what happened is that I downloaded the shader compiler and it would crash. So I had to use some environment variables built into Mesa to then get back that information. So it was a big pain in the butt. If only they had that tooling inside the Vulkan SDK and we could just go full ham with it. And then it would be there'll be more quality assurance around it, right? Because it would be regularly released in a more public manner. And that's what I hope they would actually do. Because they're kind of slacking there a bit, I think. Because it kind of sucks having to compile these pipelines and stuff all the time. It'd be good if they could be pre-compiled with an offline shader compiler. Even if you couldn't ship with it and it was only in debug, that's okay. Right, I'm just going to take a quick break and get another drink, and then we'll do this lovely stack thing. And yeah, I need to figure out how many VGPRs we got as well. And yeah. Right. BRB. Alright, welcome back everybody. One day we'll have nice things, yes, one day. One day. Boom. Yes, I think I remember seeing we only had like 64 VGPRs. RDNA 2. It's a pretty cool name, not gonna lie. PDF. PDR? What? How many of those VGPRs do we have per? We're not talking about allocated. Oh yeah, there was 1024 VGPRs in... Forget the number of VGPRs. I think it was 64 VGPRs. Up to 1024 work items, 16 or 32 wave 32s can be combined into a work group. 32. So I think it's 1024. Is it only 32 VGPRs then? Because then if I did 1024 divided by 16, yeah, that'd be 2 wave. Oh wait, where am I getting this? But yeah, there's a chart somewhere. I remember seeing it. Yeah, 1024. Oh, I remember doing the maths. There's a certain thing about it. So you've got... So you got to remember with a VGPR, yeah, it's got 32. Interesting. So what is times 32? Okay. Why is it times 32 though? Let's figure out how many VGPRs there are. So RDNA2 is the card that I have. I'm just trying to make sure that it runs well on that. And then the ones that come out in future should be fine. TM. Right. In wave 64, each wave may declare n normal VGPRs. The wave gets 64 times n D words. Yeah, so when you have one VGPR, you'll get 1 times 64 D words, right? Because each thread needs a variable, a register, right? But it's in a SIMD, or in 2 consecutive SIMD. Well, yeah, it's in 2. Yeah, 2 SIMD units can read from that VGPR memory and pull that into the SIMD units, run the instruction or instructions, and put them back. Yeah. Right, we're in instruction territory right here. What's going on? It's encodings, operands. Where the hell are we in the scroll bar? We're only at the top. Oh shoot, I moved to the top. It might be in the workgroup processor. Right, so where is it? It's the workgroup processor. You've got 2 SIMD unit. Each workgroup processor is, yeah, LDS memory of that size. Right, that's LDS. Why am I reading that? Global data share, not reading that. Where is... Yeah, I forgot if the number is 32 or 64. You know what? I can figure out what it is in my UI shader. We should be able to find out. Because in my UI shader, I should have this number written down. Right, I've got another stack thingy somewhere. Right, there's a distance operand stack. That's 6. It's quite low. It must be 32 then. I think it's maybe 32 VGPRs and... Oh, we can probably find out if I just compile it. Yes, we can. So there's a Mesa thing. Mesa... AMD environment variables. We can get back the source code. And the VGPR count and all that. Where's the AMD one? Radeon. Right, so we want to, can we see a disassembly of the... Use SB shader dumps. I think it's that, let's figure it out. Ah, it's right here. Shader stats. Perfect. Right, let's try that out. There we go. Right, so here's the shaders. So there's a UI shader. Yeah, the thing is, I don't think it tells you the number of... Yeah, it doesn't tell you the name of the shader. It's so we might have to figure out which one it is. Crap, I forgot about this. Hey Regilla, how you been? Obviously all compute shaders. Right, so if we go to VGPR. So that one uses 16 and it's got 128 VGPRs. I think 128 is probably common because 64 bytes, sorry, of it is my push constants. So 16 VGPRs is low. Yeah, you don't want to spill. There's 48 here. There's 32 here though. Oh man, it's hard to know which one it is. There was a 48 one, but that's not it. There's another 32. There's a 96 one here. Yeah, I forget the number. I think there's a way to get the disassembly as well. We're at V, this is it. So we did shader stats. But when we shader stats, it doesn't give you the name. There's also dump shaders as well. Let's try that one out. So it dumps the full shader code disassembly. So this should tell us it. Oh, there's no VGPR. Oh, obviously the instructions contain the word VGPR. You could probably tell the biggest number VGPR in your thing, but that's not the right way to go. So this is IR, compiler IR, it's probably mir. But yeah, this is the actual shader instructions and stuff. I don't think that's going to help us either. Well, I could just look at the datasheet and find out. Maybe it's just 32 because if you got 1024 and you have 10. Yes, that gives you 32. I can't remember the number now. But yeah, I guess we can tune it later. Let's just carry on with actually getting it working. So there'll be a number basically. So the BVH references, this is our stack. So our node stack. Now I don't know the number, but we'll define it here. So let's just say there might be a node stack capacity of 16. So we've got to be really careful. Hey Cranston. Doing well, would you do awesome? Good to hear, my friend. The code on suggest, I think you asked before, do you use the the object label? Yeah. Yeah, or at least the function name, the entry point name, there's an entry point name in your shaders. They could just use that, right? And maybe the file name or something, I don't know. Well, there's no file name. Yeah, at least the entry point. I guess most people will just have the main entry point name anyway. Whereas for me, I've got different entry points. Because I put all my shaders in a single binary. But yeah, so I don't ever use the object name thing. I use it for the... But yeah, that's a good point. There's a debug object name here, but I don't know if the driver would be aware of this. Oh, I've already done it. Yeah, I use it for the shader. Yeah, I've got that in there. So when it creates a compute pipeline, which is a shader, it will give it an object name. Yeah. So, yeah, I'm not sure if there's anything else. Hey, Master Agent, how you doing? Good to see you. So I think the algorithm is going to be, you check, did I hit it? Yes. Put it on the stack. Check, did I hit it? Yes. Put it on the stack. Right, you do that if it's a parent. And then if it's a leaf though, you will add it to the closest hit thing, right? So this stack might actually have to get bigger. Yeah, gotta be. So yeah, put it on the stack. So this would be one that has, yeah, then you look over all the children and you only put parents on the stack. So for everything that's on the stack, there's a potential of 4 children nodes to look at. And whatever is underneath all of those. So maybe this doesn't have to be too big. It has to be big enough though. Because, well, depending on how deep it goes, right? You could have, like, you could have checked this. Go down here, yeah. And come up and go down again. Yes, depending on how deep it goes, you need. But yeah, 16 should be right for us at the moment. Right, so let's actually get going on it. So the first reference you get, so we can have the ref here, we could poke it in. And then we get these things, chuck them in here. So we want a stack index. So the stack index, you always, what do? Is that the insert place or is that the read place? It's the insert place, I guess. Read take 1. No. I don't know. So you basically read from here, node stack. So when we write, we can have a bit of safe code, I reckon, to make sure it doesn't overflow. So you get the number of children out, you go over all the children, and you go, oh, if this thing is a parent, and I've hit it. So you do the testing. Have I hit it? And then you say, if it's a parent, just chuck it on the stack. The node stack. Great. So node stack index. So you bump this up by 1. Now, we'll put a bit of safety code in for now. If that is greater than or equal to the BVH node stack capacity, we're going to go ahead and return, and then probably do one of those super lovely prints and be like, whoops, overflowed the node stack, cry face. And we have to put in something to print because my macro is a recursive macro and it doesn't optionally do the last thing. Right, then we poke in the child. So of this node. So how does one do that? Well, there's a BVH node, BVH ref, yes, BVH children count, that's the last one. And then there's a BVH children start index, I think it's called. Children node start index. Damn it. Child node. Children nodes start index. Right. Excellent. So that will then put it on the stack. Else, do some shading, man. We've reached a leaf. And then update the closest hit. Interesting. So you can remove that breakpoint. So let's have a think about it for a sec. So probably remove that now. Right, let's think about what we've just made. So we've got maximum iterations of 64K, and we're going over all of the children getting. So this will start at the root node. The root node goes in there. You go over all the children, and if you get some hits, you pop them on the stack. You should have taken this one off the stack, not gonna lie. So you put that on 1. You take away. And then we should have another statement to say, another assertion, basically. To say, oh, by the way, if this has to be greater than 0, if not. Whoops. Underflowed stack. Right. That's interesting. Yeah, BVH means bounding volume hierarchy. It basically means, yeah, you can, it's an acceleration structure, so you don't have to test against every object in the scene. Instead, you can traverse down a tree and try and do as little tests as possible. Oh, check after? Wait, do I want to check after? Oh, for these things as well, the indices. Yeah, they're in bounds. Good idea. Yeah, check these two things. That would be a good idea. Don't want to blow up the GPU. Working on a save game editor which is generated in or which is integrated into my game, bringing the power of modding to whichever platform I decide to release it on. Awesome. Initially, my goals were just a tool so I could corrupt save data at will, testing purposes. Nice. Yeah, that sounds great. Yeah, so people can edit their save games and get to where they want and that. Is that going to unlock after you've earned it, or is it just going to be there from the get-go? Oh, yeah, it will. I'm too busy thinking it like an assertion. Yeah, it's equal to 0 underflow. Good idea. Good idea. But yeah, I always get my booleans the wrong way around. I think it's one of my number one reasons why my code doesn't run the first time. So we should probably check this bound wise. What's the number of BVH nodes we got? So this could just be a constant. Wait a minute, what the crap is this? What? This is number of build nodes. We can save some memory. So this could probably be a constant, not gonna lie. But we probably want to make this scale across different levels of hardware, so we should probably have... Or do we? We're probably... No, I don't know. If I have it as a constant, I can also put in the shader. So I'm trying to work out the number of total build nodes. So build nodes capacity, that is the number of leaf nodes, take 1, plus the number of leaf, because that's the number of internal nodes, plus the number of leaf nodes, right? Pretty straightforward. So that is this. Then the number of BVH nodes in this one has up to 4. So that's for a binary tree, but for a quad tree, so it's divide by n take 1. N meaning the number of children. So obviously that's divided by 1, which then cancels out for this. Oh, and then it's a divide by rounded up as well. So yes, a rounded up divide. So this is divided by 3, but you've got to do like a round up. So you got to add 3. I think that's it. So have a look at some other logic. I've done it in the past. Oh, it's the take one. Hang on a minute. Why is it the take one before? Oh yeah, then divide by 1. Okay, I got it a bit wrong way around. If it's take 1 before, then add 3. I guess I'll just do a take 1 then plus 3. There's maybe a plus 2 then, but it won't be really round up then. Right, I think that's the logic. It could obviously be simplified, but that's cool. That's what compiler's for. Right, so back to where we were, that just goes in there like that. So, yeah, nodes capacity. So we've got a number of possible nodes. And there's a maximum number of nodes in a BVH in the buffer. So that's for a single BVH. Excuse me. Right, so that's also another constant now. And voila. So we can now put that in the shader, basically. We can now just say, well, if is greater than the number of nodes, then we've clearly so you have a start index followed by a children followed by a count. And then followed by a and then followed by a nodes cap. That's quite a lot of stuff. That's a big string going into the terminal, but well. Yes, I'm just doing. And then. Oh, looking good. So that's a good check too, so the CPU doesn't, or the GPU doesn't crash and burn. I was thinking of having it from the get-go, but keeping it hidden via enable via settings editable in the game settings menu or something. Right, okay. Yes, have it kind of hidden, but people can access it. That's not bad, I guess. Wait, why is there a second one? Yeah, why have I got this here? I think I copied and pasted that one twice. I pasted it twice. Thank you, Larissa. I appreciate it. Yeah, maybe I was thinking about writing these as separate things. Alright, no one knows what pass meal is going to do. We can only speculate. Alright, so this is looking better and better. We've done the adding to the stack, right? So after you've searched all of the children, what do you do next, right? So I've searched all of the children. Then I go back around in the loop and I say Wait, do you even need this? Do you just say if this is 0, just get out of here, right? You've already looked everywhere. Yeah, because you'd have stuff on the stack, and you pop off and carry on. Yes, I think this is kind of silly. You just basically, this exists for a reason. It's the end. And obviously that could probably just go into here, to be honest. Ta-da! So I think that's everything, right? So we're going over the children, checking them, putting them on the stack. Some shading and stuff like that. Right. I think it's ready to go. So if the stream dies, we'll be right back. But we shouldn't die, right? It's all safe. See. Right. Clearly slow. Tons of traversal right, it's being 5 milliseconds, being 42 milliseconds. And I can't see any printing. So we have to think that it's probably hitting the max number of iterations. But I don't know. So what we can do is we can figure that out. Right? Taking a super lovely if statement. And again, I have to print it out, right? Because that's just the way my macro works. Or my printf works, it's a macro. There's the for loop over everything. That needs at least 2 things. So I need to pull that out. And it's called iteration, not iterations. Overflowed the node stack. Oh, somebody forgot to put a new line in their printfs. Past me, what am I like? So it turns out I put a bunch of prints without damn new lines. And we overflowed the stack so soon. Isn't that a shame? Need more VGPRs then. Something must be weird if we keep upping. Like, why do we only need... Like, we've only got 32 nodes at the start. Why have we got 16 parents on there, you know? I'm a bit confused about that, to be fair, but let's up it anyway and see what the crap is going on, because something's a bit weird about that one. So I only had 32 nodes. Whoops, hit max iterations. And then another time, node stack. Right, so clearly there's funny business going on. So if you overflow the node stack, you hit return. But you shouldn't be rendering any pixels if you hit returns. Also confused. So why don't we just try and render everything, eh? Wouldn't that be a bit of fun? Let's break down the else. and just be like, no, render everything. So we're just going to be seeing ellipsoids everywhere. Right, we should be back. Let's get priorities right and get some music back. Oh yeah. Yeah, I did not know how that happened. All I did was uncomment something which was a little bit more expensive, right? But, well, a little bit. It's PBR. But, right, source code is still there and intact. It's alright. So what happened again? I would have done... See, maybe we hit some memory, invalid memory or something. That was not... Yeah, it seems like we're hitting some invalid memory. If we're going... Bow, wow, wow. Like, was able to ray trace successfully against two things. Two things, you see. So we could... So it's going to push on two things. And then... So something to keep note is we're not providing an offset. But it doesn't matter because all our nodes are at the beginning. But if we add multiple BVHs, it's not going to really work. So for this BVH that we're ray tracing, there is kind of like a base offset that we need to be applying. So we should put in here BVH root node index. It's not really the root node though, but it's like BVH base node index. That's probably a better way of saying it. Base nodes. Base node index. I don't know. Words. They are difficult sometimes. So if we get that reference in this case here, we can always update this thing when we add instances and whatever, but we need to be, when it comes to producing some kind of so the funny thing is as well, right? It must be the PBR code, which is doing the out of bounds access. But it's got a map. The BDRF should be fine. And it accesses a so accesses the cube map, which you can't go out of bounds of that because it's a vector. Maybe the vector could be invalid. Or I don't know. Yeah, you just access a couple of cube maps. Or it was just way too expensive that it just ended up taking more than a couple of seconds, and therefore it was too long, and that's enough to freeze the GPU because the drivers suck. So yeah, so what can we do to run it? So really I should have incrementally built this thing, but building the bigger version seemed quite simple, right? Just add a stack. So we could say, stop at level 2 and let's just render all of it and see what happens, right? Let's go 2 levels down. So we're going to do just that. How do we know if we've done 2 levels or not? Well, we can simply put a maximum number of iterations which resemble which resembles the capacity that we're looking for. So if we've got 2 nodes, well, yeah, because this iteration is going to go for the root, and then the left hand side, and then the right hand side. So that should only mean 3. Right? So that should be everything we're looking for, I think. So if we just cap it to 3, and we just try and render all of those, we should see... Also, I guess if the children count is greater than... We kind of want to know if there's any invalid data, perhaps. So if that's greater than 4, or less than 2, that's something worth knowing about. What else is worth knowing about? Let's take a look at the... So the BVH node type is also worth knowing about, like BVH node type node. We want to say, well, that's got to be, if that's greater than or equal to, was it 3 or something? I guess I can just do the last one myself. Then we put that in there like that. We should probably put the node index in there as well, but that's all right for now. What's another one? That could be very problematic. The sizes of things, probably not so much. We should check if they're out of bounds, though, to be honest, at some point. They looked alright. The start index would be... It's fine. They will be recognized as via this, right? So, all right. So we want to So let's do what we did again, but this time only in 3 iterations. Where's my node, man? Alright, so let's see what happens here. Fingers crossed, if the stream dies, I'll be right back, but it shouldn't do, right? Right, we're still alive, but we've got a bunch of whoops. Right, we hit the max iterations, obviously. Right, so why don't we comment that one out? That's kind of a success in my eyes right now. And it's stopping us rendering a final pixel. I see some black spheres. So these are not being rendered right now. They are being rendered in a sense that... But they don't have the PBR. Is there some printing that's happening that I can't see? Yes, obviously everything that doesn't hit the spheres gets rendered when the return happens, right, obviously. Because... Yeah, the returns only happen when there's errors. Oh, sorry, the returns is still in there. Right, let me unzero that. Right, so we're obviously rendering the closest hit ones. These are the 2 big parents, right? But we're starting to see another, there's an intersection here. There's another one there, which goes outside. So there's a bit of a... Ooh. I don't know what's going on there, to be fair. Yeah, there's an ellipsoid within the ellipsoid. That's probably okay, because this second one, it's only this second one, I think. Because there's only 2 of them that you can see. But see if you have another one poking out. That's another thing we need to be careful of, like... Sometimes the ellipsoids might not be big enough, so you get artifacts like this. Where you can see through it, because... Oh, I don't know why. Oh yeah. My closest hit T is in the wrong space. I need to move that back into world space. So you need to, that's along the ray in, yeah, so if you move it back into world space, T world space, so it's hit T. So basically you need to do the inverse rotation. So that is yeah, so inverse rotation. So I think that's just quaternion, or yeah, that one. The second makes it go the other way around. And then you mol v, and then you apply the translation. So there's this sort of subtraction here. You need to apply the center position world space onto it, I think. No, what are you applying? Yes, we've subtracted the center position from it. So if we add it, it should go back. No. Yeah, I think we... Or maybe we add first. I think we add... I think that's right. It doesn't matter right now because our rotation's broken anyway. But I think we add... If you add the center position of the... Wait, where's that Milton graph gone? So originally this was in world space and this is in world space as well, this position. But we wanted to make it such that this is origin 0, 0. This is an ellipse, by the way. Here's the camera. So to make it such that we have a vector, aka a position, of relative from here that goes to where the ray origin is, we need, so we did the subtract, right? We subtracted the center position of this from that position there, and it got us that vector. So if we add it back, it will then produce a vector going from the world origin back to there. But then imagine you've got your t. So you've got your ray origin there going that way. You've got your t, which goes down there, I guess. So you got a point there, and you've added. Say if world origin is here, you've your vector going there. You've taken the difference and produced. These are terrible drawings. So world origin, you had your world space position for that, world space position for that. You did a subtract, so that's your local space position of this now, right? So if you had your t, which is here, maybe let's do it a bit further. Let's do it here. There's the hit point, right? Obviously. Now the hit t is there. Oh yeah, we're talking about hit t, aren't we? Crap. Yeah, so you need to translate the hit position back in the hit position. Where's that one? Yeah, I shouldn't have got t back, to be honest. But there is a hit pause. Yes, there's a hit pause. And then we length it again. So hit pause. So and then if you add this vector to it. So you've got a vector going from there. Yeah, that doesn't make too much sense. So you want that vector. That's what you want. But you've got this vector going to there, and you've got the vector going from there. But you really want to subtract this. So, oh no, sorry, you've got the vector in local space going from here to here. No, you haven't. Position relative from here, isn't it? Yes. And you've got this one here, right? Yeah, so this... Yeah, this vector added onto that vector, which is here, right? So that's this vector here. There's too many arrows. This vector here is hit pause, and then that vector there is center position. So that'll get you this hit point here in world space. Perfect. And then you want to do some rotation on it as well. I don't know what the rotation order is, but I think it's after. Cool. And then you want a length. Wait. You get T. Hit pause from where? Right, and then you take the diff. So you're going towards the hit position from the ray origin in world space. And then you length that. And that's your... So hit pause world space. We need that for the proper shading anyway, right? Bum, 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 bum. Things. Right. And then you length it. Right, so the surface normal. How did I miss the normal? How do I do that? Normal n. Hit pause divided by R2, R2 squared radius. So we'll have to regen that. It's quite easy. No, but it's hit position relative from the center of the ellipsoid. Right. So you just translate. So it's just a rotation, basically, on the... It's the inverse rotation. So yeah, we can just do it all up here. It's quite easy. So what is it? Hit normal. And the hit normal is the inverse rotation. Hit dot normal. So make sure we're not using hit anywhere else because that would be silly. So hit pause world space and then hit normal. And voila. Hit T world space. So that should be all of that corrected. So maybe that fixes that glitch that we saw, but I don't know. We'll find out. So we see the oh, they're very small. But if we change the tree configuration, yeah, we're still getting sort of... Oh boy. Yeah, the closest... I think our T might be the wrong way around. Is it kind of like a negative thing or something? Like we should be... No, it's in a length, isn't it? Not sure about that, to be fair. Say if we capped out to 2 or to 1 iteration. So that just runs the once. They'd only get the 2 ellipsoids. And I'll be trying to render ellipsoids inside the other ellipsoids. Do we get that sort of glitch? So I think it's because the ellipsoid is inside the other one. There's something a bit weird about it. I can't see it there, to be fair. So we did 2 iterations. That allows for... a little bit more to be rendered. So maybe we say we're only allowed to render if you're on the final iteration. That'd be a bit strange though, wouldn't it? See what happens there. Do we see anything? Right, so these are on the final iteration apparently. What are we seeing? See, this, I don't know if this is the parent node. It can't be, because it's only rendering the, it's only going over a set of children. Oh, what is this doing? It's storing a depth in... we're not storing a depth anymore, are we? That depth should be in view space at some point. Yeah, we read a depth out in other places, I think. But yeah, we should be storing a depth into a buffer. How's it going? Good luck figuring this out. Thank you. Have a good evening, Larissa. Good to see you, as usual. But yeah, I'm not sure. Yeah, so we could maybe do a depth thing. The issue is with depth. See, depth information might be nice for debugging. Like obviously in cases right now. Like I want to stop the tree at a certain depth basically, isn't it? But we don't really have... We could use the BVH node ref as that depth. What's all the depth in there? And then that would mean... Yeah, why don't we do that? That sounds pretty sweet. There's also encoded a depth value in there. By depth, I mean like how many levels down on the tree. So we could... You only need 16, right? So that's 4 bits. I think so. Right, so yeah, that needs to be 6 bits to the left. 2 bits to the left. Well, sorry. 4 bits to the left. And then board width, depth, and 4 bits, right? Yeah, so I use 16. So this would then be shifted right 4. Shifted right 6. And then depth. The depth of that is what? Well, shift right 0, but it's just and of... Right, so we find where we make this reference. We make it on the CPU once. We should probably store this in GPU memory somewhere really, but depth of 0. Yeah, we're not going to search over the whole tree, is it, as well? We've got to be careful of that. Right, so make a ref here. So you know the depth, right, when you pull out the... Yeah, the depth is here. So we go, oh, if the depth is... See, depth is a bit of a terrible name, to be fair. I want to call it node depth now. So you say the node depth is greater than... max node depth, we could say... Right, just get out of there. We've reached the max node depth. Maybe just say break. And we say, well, if you're at the last node depth plus 1 equals max node depth, then render. So why do we do that node ref thing here, right? So it's just node depth plus 1. Like that. So it'll be maximum of 16. Alright, see how that goes. So we're seeing an edge of 1 here. When we look at it from different angles. Oh boy. Right, so part of me wants to make these guys bigger or change the camera speed. Because we can scale these a bit. Scale them by 4. Make him a bit bigger. So that should have something we can move around a bit better. So yeah, kind of. Right, so something else we can do is we can render a debug version of the parent hierarchy, and we can also get a slider up here to say, hey, because I did this in the previous one, should we try and render a bunch of because you can render some outlines basically based on the local space normal. You could say, hey, if my normal is whatever, render and if my normal is pointing directly on an axis, or roundabout on an axis in local space, then render that line. That's something we can do. So you'll be able to see the parents of the nodes as well at the same time, but they won't be obstructing the other nodes. And then that way we can tell, like, oh, this parent is actually too small, or something like this. But it could be equally be the translation code between the spaces. I wonder what my rotation is, to be honest. It should be an identity. It should be identity. So 0, 0, 0, 1. It's gonna be a bit overkill. There'll be a lot of stuff coming in the terminal, but it'll be alright. Right, that's a bit off, but so that's because of the precision, how we quantized it. Yeah, that's to do with how we quantized it. It's a bit off. Rotation it can't be the roundup, can it? I don't think it's the roundup. Yeah, now that's gone over, that's not good. So we convert it from -1 to 1 to 0 to 1. And then we multiply by 255 and then turn it into uint, which will truncate it to 255. And then so you should get the round down. I wonder what these are. There should be, are there a bunch of zeros? Zero, 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 basically. Crap. No. Wait, is this in, right, CP doesn't like it. What? Engine, GPU, shared. I've already got it. Oh, it's in, right, it's in another header file probably. Probably in this header file here. GPU shader. Well, that's great. So if I move that to the actual shader code, it'll work. Right, see what we get there in the 128, 128, 128. That's fine, isn't it? Because that'd be 0.5, which is 0. Oh, did I not multiply it by... No, I must have done. Yeah, there's a times 2. So yeah, it'd be a little bit over 0 because you'd get 256. So there's no perfect 0, I think. Something like that. So if we changed it such that we lost 254, for instance, right? Bit of a weird one. But if we did that instead. So you should get 127 there instead. Yeah, and then when you use it in the shader, do you get a perfect 0? Yeah, you get a perfect 0 now. Right, it's a bit funny. Yeah. Well, that will definitely need a comment because people will be like, oh, that's a typo. But yeah, then you get perfect 0 at least. $254 is not a typo. It's so we can get quadlet. It's so we can encode 0.f d/encode 0.f and get a perfect identity, right? Cool. Nice. Yeah, but I don't think that was a problem to do with anything that was going on. It could be though. Yeah, that won't do a rotation now. It's interesting. Interesting though. Where's the other print? Yeah, let's delete that. So that's sweet. Yeah, we're still getting these issues. Look, if I look at it from here, whoa, go around here and it cuts off. Very view dependent. So I feel like that's transform related where, yeah, it's like anyway. Yeah, I feel like it's transform related with something to do. Yeah, how we're translating to local space and then back out is slightly off. Or not slightly, it is just wrong. So yeah, something to do with that conversion. Yeah, that's something for next time because I've got to get going now. But yeah, so on Sunday we'll carry on with this. We'll investigate further into these things. We do have debug drawing capabilities, so maybe it's best to debug draw what is going on, and perhaps, yeah, we can target a single ellipsoid, debug draw it, and figure out what's going on. That's probably the next best step. Not sure why I didn't think about that API. I completely forgot I have the API. That's probably why. Yeah, that'd be awesome. So let's find somebody to raid. Yeah. Dark mode. What's going on here? Alright. But yeah, have a great start to your weekend, everyone. I'll see you all on Sunday. Or we'll carry on with BVH ray tracing from compute shaders. Oh yeah. Where is... Oh, I'm following people. Obviously, last miles. Let's go. Right. Have a good weekend. If you want to come and hang out in the meantime, we have a chat. Discord. Come join it. And talk about programming. That'd be cool. Right. Have a good weekend. See you all on Sunday. Bye-bye.